Welcome to our video on pressure. The next one in pressure. We've just done pressure in liquids, so this is all about pressure in gases. We're going to link pressure and volume. We're going to use a formula to calculate changes in pressures and volumes, and then we're going to talk about the Earth's atmosphere and talk about atmospheric pressure. So quite a lot to do. First up, a little video. If you can see in this video what happens to the pressure when the volume changes, as in this animation. So you can see that I've put in a certain amount of gas in a particular volume, and we've kept the amount of gas the same, but then we've increased the volume. So if I just start it again, there in goes the gas at a particular volume. The gas has stopped going in, and then we increase the volume and we don't add any more gas. Okay, now the idea for the first 5 minutes or first couple of minutes is what happens to the amount of collisions against the sides of the container. So if we just play it one more time, let's just think about what happens to the amount of collisions against the sides. So think of all the collisions there, and then as the volume increases, how many collisions are they now going to have? Okay, so if we move on, this is all something called Boyle's law, and Boyle's law relates the pressure of a gas and its volume, and this is what we're going to be trying to be doing. We're explaining what happens to the pressure of a gas as its volume was decreased, but if the temperature's kept the same. So in the previous animation we increased the volume, but let's just consider now what happens if we decrease the volume. But remember, all along this we are keeping the temperature of the gas the same. And if you remember from your work on temperature of gas, then the temperature of gas is all to do with how fast the particles in a gas are moving. So if the temperature, let's just follow the logic through, if the temperature of a gas is the same, the speed of the particles is the same. So if the speed of the particles is the same, the force of each collision is also the same. Okay, so that means each individual collision applies the same force on the side of the container. But if we decrease the volume, then there's going to be less distance between these collisions. So in the previous video we increased the volume, so there was with an increase in volume there was going to be a bigger distance between collisions. But now if we imagine we're decreasing the volume, there's going to be less distance between collisions. So therefore there's going to be more collisions in any 1 second. And if there's more collisions with the same force, that means the pressure is going to increase, because all of those individual forces add up, and if there's more collisions, then all of the individual collisions add up to be more force, which means the pressure is going to increase. So just to demonstrate this, just imagine one particle. Now each of these boxes has got one particle. They're moving at the same speed, but because the one box is smaller than the other, it's having more collisions. So the bigger box, we seem to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, whereas on the smaller box we are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I counted to 10 much faster. So there's going to be more collisions in the smaller box. Okay, this is the fundamental idea. Here we're going to say if we pull up on this, if we trap this gas and they're all moving at the same temperature, and we keep them moving at the same speed, so at the same temperature, if we pull up and increase the volume, this is going to decrease the pressure because these will have less collisions, whereas if we push down and decrease the volume, then this is going to increase the pressure because they'll have more collisions. And it's all to do with the amount of collisions. Okay, now another little animation we can do. We can now try and put some numbers on this. Here we've got, again, a container. We've got a gas in, and their temperature or speed is constant. And we're in, at the minute, we're in a fixed volume. Okay, and we seem to be in a volume of 140. This is the volume. This measurement is 140. And our pressure, if we read the pressure gauge, is 1. So over here, we've got a pressure of 1 in a volume of 140. Now, if we multiply these two together, we'll get 1 times 140, which is 140, but we'll come back to that in a second. Okay, now if we reduce the volume, and this time I'm going to halve the volume, so I'm going to halve the volume down to 70. Notice these are still moving at the same speed. We've kept the temperature the constant, but if you look what's happened to the pressure's now gone up to 2. Okay, so our pressure is now 2 when we've halved the volume to 70. Then finally I'm going to take the volume all the way down to 35, and you can see the individual particles are moving at the same speed, but now there's going to be more and more collisions. all at the same speed. They were all with the same force, but more collisions with the same force. And you can see we've reduced the volume to 35 and the pressure's gone up to 4. So 4 and 35. I'm not sure why that says 34. That should say 35. Okay, so if we multiply these all together, 1 times 140 is 140, 2 times 70 is 140, 4 times 35, forgive my mistake, is also 140. So what we are saying here is that for a fixed mass of gas held at a constant temperature, which is the speed, remember, we know that pressure times volume is a constant. Now this is on the data sheet, that pressure times volume is a constant. Okay, now because of this, from the equation PV, pressure times volume, is a constant, we know that if one goes up the other goes down, because if these two multiplied together, pressure times volume, is the same number. If you increase the pressure, you decrease the volume. If you increase the volume, you decrease the pressure. And that's what this first graph is all about. If you plot a graph of pressure against volume, it looks like this. And notice if we increase the volume on the bottom axis, the x-axis, then the pressure comes down. And if we decrease the volume, the pressure goes up. Now this is what's known as inversely proportional, and we can write it like this. We can say pressure is proportional to 1 over the volume. This is what's known as inversely proportional. You might have done that in maths. So a graph of pressure against 1 over the volume should be a straight line, because if we plot instead of V, 1 over V, like on this graph, if I plotted 1 over the volume, this will mean it's a straight line because we know that pressure is proportional to 1 over the volume. Okay, now what you can do loads of examples, and I've got a big table here, so if you want to pause the video and try and fill in the missing blanks, I'll just do the first one for you here. So pressure times volume, so 100 times 24, if we did this for the first gas, that pressure times volume is a constant. Well, here what we're saying is in the first one, PV is a constant, so 100 times 24 must be equal to V2 times 200. Now look here, the temperature is 22.5, the temperature is 22.5, so because we've kept this gas at the same temperature, we know that pressure 1 times volume 1, 100 times 24, must be equal to pressure 2 times volume 2. And if you look, we've doubled the pressure, 100 has gone to 200. Okay, so if we've doubled the pressure, you might work out that we're going to have to halve the volume. But if we do it mathematically, look, 100 times 24 must equal V2 times 200, this times this, V2 times 200. So you can see that we've got 2,400 equals V2 times 200. If we sort that out mathematically, we can say that V2 equals 2,400 divided by 200. If you put that in your calculator, you get 12 centimetres cubed. And some of you might have said, okay, I can see that because I've doubled the pressure, so I halve the volume, so that will be 12. Okay, now there's loads of these. Look, I've got 2, 3, 4, 5, 6, 7, 8. They're all fairly straightforward. If we just look at the last line, the pressure's gone from 200 to 100. So this time we've halved the pressure. So the volume has gone from 24 to 48 because we've kept the gas at the same temperature. And remember, this expression or this equation that PV equals constant only applies if you keep the temperature the same. All right. Okay, so a couple of lessons ago we might have talked about this. This is the collapsing can, or you may have done it in school. And what you did, you heated some water inside a can and you very quickly inverted it and put it in some cold water so the gas inside the can cooled down. Because the gas inside the can cooled down, the pressure dropped, and this drop in pressure caused the atmospheric pressure to crush the can. But we didn't really say anything else about atmospheric pressure. All we said was that atmospheric pressure, the red arrows in our diagram, crushed the can. So before, when there was air inside the can, the red arrow pressure was equal to the blue arrow pressure, whereas when we remove the air or decrease the pressure of the air inside the can, the atmospheric pressure was able to crush the can. But we didn't say anything else about this, but here's the idea. If we imagine this, if you think of yourself at the bottom of a mountain, the person at the bottom of a mountain has got a lot of air. All of this air is on top of the person all the way up through the atmosphere, whereas the person on top of the mountain hasn't got much air on top of them at all. So this box here is saying there's only this much air above their feet level. whereas this person, all of this air is above their feet level. So when you go higher up, the pressure decreases. The higher up you go, the more the pressure decreases. And this is sort of similar to what we said in the previous lesson about depth. When you go to the bottom of an ocean, the further deeper you go, the more the pressure. And that's just the same if we imagine our atmosphere as being like an ocean. The deeper you go into the atmosphere, the lower down you go, the higher the pressure. Okay, so just to make sure you've got that, let's just see. Air molecules colliding with a surface create atmospheric pressure. The number of air molecules equal to the weight of the air above a point on the surface decreases as height increases. So the number of air molecules above you decreases as height increases. So as height increases, there is always less air above a point there is at a lower point. So the higher up you are, the less air you've got. So we can say that atmospheric pressure decreases as height increases. And a couple of extension questions. Which is hottest? If you boil water in the classroom at school, or if you boil water at the top of Everest? So applying what we've just said, if you boil water at the top of Everest, then there's going to be less air pressure. So on the surface of the water that you're boiling, there will be less pressure, so it's going to be easier for the water molecules to evaporate into a gas. If it's easier, they require less energy. That less energy means the boiling water does not boil at 100 degrees Celsius. It'll boil at much less than 100 degrees Celsius. And in movies, you might have seen, why does everything get sucked out of a plane when the door is blown open at high altitudes? And this is the classic scene where everyone's been sucked out of the plane window. Well, when an aeroplane is at high altitudes, outside the plane is very low pressure, but the plane has to be kept at a higher pressure for the people inside. If the door is opened, it's much higher pressure inside the plane than it is outside the plane, and with the door being open, all of the air inside the plane, all of the air pressure inside the plane rushes out through the gap, and it tends to take things, people, objects with it. So that's why it looks as though everything's being sucked out of the plane, but really it's all of the air rushing out of the plane because it's a high pressure inside and a low pressure outside.